Please subscribe to support the channel. There are stars scattered across the night sky that dazzle us with their brilliance, stars that have fueled myths, guided explorers, and inspired generations. But there is one star, hidden from the naked eye, tucked away at the very heart of our galaxy, that defies our ordinary imagination. A star that does something no ordinary star should be able to do. It dares to dance in the most dangerous place in the Milky Way, right beside a supermassive black hole. This star is known to astronomers as S2, but many call it the Immortal Star. Why immortal? Because in a cosmic ballet where one wrong move could mean instant destruction, S2 has survived countless encounters with a monstrous gravitational force that should have torn it apart long ago. And yet, it continues its orbit, as if mocking the abyss. Think about this for a moment. At the core of our galaxy lies one of the most extreme objects known to science, a black hole so immense that its gravity shapes the motion of everything around it. This black hole, Sagittarius A, is not something we can see directly, because black holes swallow light itself. Instead, we see its influence, stars whipping around it at incomprehensible speeds, their paths curved and distorted, revealing an unseen but undeniable presence. And among these stars, S2 stands out like a fearless adventurer, venturing closer to the black hole than nearly any other known star. It is a cosmic daredevil, completing its dangerous orbit over and over, while we watch in awe from 26,000 light-years away. Today, you're going to hear its story. A story of gravity so intense that time itself bends. A story where light stretches and warps, where speed rivals the limits of nature, and where Einstein's predictions are put to the ultimate test. This is not just science, it is a glimpse into the very machinery of the universe. So, as we unravel the tale of S2, the Immortal Star, you'll learn why this single object, orbiting in a perilous cosmic neighborhood, may hold the key to unlocking mysteries about black holes, spacetime, and the very fabric of reality itself. If you were to step outside on the clearest of nights and gaze up at the sky, you'd see the hazy band of light we call the Milky Way stretching across the heavens. It looks like a faint, milky river, a soft cloud made of countless stars. But to us today, we know that this glittering band is the combined glow of billions upon billions of stars, woven together into a massive disk, the galaxy we call home. Yet, within that breathtaking expanse, the true heart of the Milky Way remains veiled, as though the universe deliberately hid its deepest secret behind a curtain. The core of our galaxy is not something our eyes can ever truly behold. From our vantage point here on Earth, the center lies in the direction of the constellation Sagittarius. You might point a telescope that way and hope to see something extraordinary, but what you would actually find is a thick barrier, colossal clouds of dust and gas stretching across thousands of light-years. These clouds are opaque to visible light, absorbing and scattering the very wavelengths that our eyes depend on. To us, the galactic center appears completely dark, hidden behind a wall that seems impenetrable. The irony is that the most dramatic and energetic place in our entire galaxy lies just out of reach of ordinary vision. But of course, astronomy is not limited to human sight. Over the last century, we've learned to see the universe with different eyes. Infrared telescopes pierce through those dust clouds, radio observatories pick up faint signals from deep space, and X-ray detectors reveal the ferocious violence of cosmic phenomena. With these tools, we've managed to lift the veil and peer into the galactic core. And what we found, there was nothing short of astonishing. Imagine a place packed with stars so densely that they orbit like fireflies in a jar, their light intermingling, their paths weaving around one another in chaotic harmony. The galactic center is a crowded, turbulent region. Stars swarm there in numbers that defy comparison to the quiet suburbs of the galaxy where we live. Some of these stars are massive and short-lived, blazing with intense light before exploding in spectacular supernovae. Others are old and red, nearing the ends of their lifespans. And in between them are remnants, neutron stars, black holes, and other exotic objects, swirling in gravitational orbits that reveal something profoundly strange at the center. When astronomers first began to chart these stars decades ago, they noticed something curious. Their movements were unusual. Some stars zipped through space at speeds far greater than anything in our stellar neighborhood. Their orbits were tight, their motions erratic, and all of them seemed to circle an invisible point. It was as though an unseen puppeteer was tugging on them with invisible strings. Over time, it became undeniable. At the exact center of our galaxy, there had to be an object of immense mass, compacted into a space far too small for an ordinary star cluster. But even before those discoveries, humanity had long suspected something extraordinary lay hidden there. The brightest radio source in the constellation Sagittarius was catalogued in the mid-20th century, a powerful emitter unlike any typical star. This source became known as Sagittarius A, and as astronomers studied its surroundings, they realized that it marked the precise location of the Milky Way's central mystery. It's important to understand the scale of what we're talking about. The galaxy itself spans about 100,000 light-years across, a disk of stars, gas, and dust. Our solar system resides roughly 26,000 light-years from the center, tucked safely away in one of the spiral arms. From our cosmic suburb, the galactic core is like the bright, bustling downtown of a great city. And at the very heart of that downtown, hidden behind the veil of dust, lies Sagittarius A, our galaxy's central powerhouse. For millennia, humans gazed at the Milky Way with wonder but had no idea that its center held something so extreme. Only with the advent of modern astronomy, and the ability to look through the dusty curtain using infrared and radio waves, have we finally begun to see its true nature. It is here, behind this cosmic shroud, that S2 lives and carries out its daring orbit. Without the ability to pierce those clouds, S2 would remain forever invisible to us, just another faint star among billions. But through the innovation of technology and the persistence of observation, we have pulled back the curtain and caught sight of a drama unlike any other. A star racing against time and gravity at the heart of the Milky Way. And this is the stage upon which our story unfolds. The thick curtains of dust hide not only the supermassive black hole but also the stellar actors that orbit around it. S2 is one of the brightest and most important of those actors. It shines in the infrared, and its movements have become a treasure map pointing directly to the dark heart of our galaxy. The irony is striking. What is hidden to our naked eyes has become one of the most important laboratories in the universe for studying gravity, relativity, and the physics of black holes. The center of the Milky Way, cloaked in mystery and concealed from direct human sight, serves as the perfect backdrop for the tale of S2. Without the cosmic curtain, perhaps the story wouldn't feel so dramatic. But because it is hidden, because it demands that we invent new ways of seeing, the discoveries we've made there feel like revelations. Every glimpse of S2 through the dust reminds us of the limits of our perception and the vast possibilities waiting when we find ways to push beyond them. At the very core of our Milky Way, where the dense crowd of stars all seem to be pulled into invisible orbits, lies one of the most extraordinary objects known to science, Sagittarius A. For decades, astronomers puzzled over what could possibly be powerful enough to fling stars around at such enormous speeds while remaining completely hidden from sight. The answer was both terrifying and awe-inspiring. Sagittarius A is not a star, not a cluster, not any ordinary celestial object. It is a supermassive black hole, the beating, though silent, heart of our galaxy. To understand its significance, we need to pause and remember what a black hole actually is. A black hole is the ultimate collapse of matter, a region where gravity is so intense that nothing, not even light, can escape. Imagine compressing an object so tightly that its escape velocity, the speed you'd need to break free of its gravity, exceeds the speed of light itself. That's what a black hole is, a place where space and time are warped to their extremes. Now, Sagittarius A is no ordinary black hole. This is not the kind that forms when a single massive star dies and collapses in on itself. Those are stellar mass black holes. Typically a few times the mass of our sun. Sagittarius A is in an entirely different league. It holds in its grip the mass of about 4 million suns, all compacted into a region no larger than the orbit of Mercury. Think about that, 4 million stars like ours, crushed into a space smaller than our solar system's innermost orbit. The density and gravity of such an object is almost beyond comprehension. And yet, despite its unimaginable power, Sagittarius A itself is invisible. We cannot see the black hole directly because its event horizon, the boundary beyond which nothing escapes, is completely dark. But its presence is undeniable, revealed through the dance of the stars around it, the radiation from matter spiraling toward its maw, and the sheer gravitational influence it exerts on its cosmic neighborhood. One way to grasp just how extreme this black hole is to compare it with the stars around us. Our Sun is about 1.4 million kilometers in diameter. If Sagittarius A was somehow swapped with our Sun, it wouldn't be some giant glowing orb dominating the sky. Instead, It would look like a black sphere, and its gravity would shred the solar system within moments. Planets, moons, asteroids, everything would be pulled into chaotic orbits or swallowed entirely. Luckily for us, it resides 26,000 light-years away, safely tucked at the center of the Milky Way, far beyond its destructive reach. Still, from its position, Sagittarius A shapes the structure of our entire galaxy. The spiral arms of stars and gas that make up the Milky Way rotate around this dark anchor. It is, in every sense, the galactic nucleus, the gravitational boss that keeps everything tethered together. Without it, the galaxy might not have the structure we see today. But what makes Sagittarius A even more fascinating is not just its size, but the opportunities it gives us to study gravity at its most extreme. Unlike the black holes we've detected in distant galaxies, this one is close enough for us to watch in action. We can track the orbits of stars, measure the bending of their light, and see Einstein's equations being tested under conditions that no laboratory on Earth could ever replicate. The discovery and confirmation of Sagittarius A as a supermassive black hole wasn't an overnight achievement. For decades, scientists debated whether the mysterious radio source in the galactic center was a dense cluster of neutron stars, a collection of smaller black holes, or something else entirely. It was only when astronomers began tracking stars like S2, whose orbits clearly revealed the pull of an invisible giant, that the truth became undeniable. Nothing but a supermassive black hole could explain what they were observing. So when we speak of Sagittarius A, we're not just talking about an object of curiosity. We're talking about the single most influential feature of our galaxy's core. It is the invisible engine around which the Milky Way rotates, the destroyer of light, the sculptor of orbits, and the ultimate testbed for our theories of spacetime. And it is here, in the shadow of this monstrous entity, that the immortal star S2 dares to dance. Over and over again, S2 completes its orbit, passing close enough to the black hole that the laws of physics bend in ways we can barely grasp. The very existence of Sagittarius A turns S2 into more than just another star. It turns it into a cosmic messenger, whispering secrets about the deepest forces in the universe. Among the countless stars that orbit in the crowded heart of the Milky Way, one has captured more human fascination than perhaps any other, a star that astronomers call S2. On the surface, S2 might seem unremarkable compared to the fiery beacons scattered across the galaxy. It is not the most massive star we know of, nor the brightest, nor the oldest. Yet what makes S2 extraordinary is not so much its nature as a star, it is where it lives and what it dares to do. S2 orbits the very monster that rules the galactic center. Sagittarius A, the supermassive black hole with 4 million times the mass of our Sun. The nickname Immortal Star arose from the sheer improbability of its existence. For a star to orbit so close to a black hole without being torn apart seems almost miraculous. Stars that stray too near a black hole are usually doomed. The gravitational tides stretch them, distort them, and can ultimately rip them into streams of gas, feeding the black hole in a violent spectacle. Yet S2 defies this fate. It does not merely brush past the black hole once, it loops around again and again, like a fearless dancer skirting the edge of a cosmic abyss. Each pass is a brush with annihilation, and yet the star emerges intact, glowing defiantly as if mocking the gravity that should destroy it. What makes S2 especially captivating is that it has been observed in detail over decades, making it one of the best-studied stars in the galaxy. When astronomers first tracked its motion, they realized they were watching something extraordinary. S2 wasn't orbiting another star, nor a cluster of objects, it was orbiting an invisible point of titanic mass. That orbit, precise and daring, became the smoking gun that proved the existence of Sagittarius A as a supermassive black hole. In other words, without S2, we might still be arguing about what lies at the center of the Milky Way. S2's courage, if we can call it that, exposed the truth. Visually, S2 is classified as a young, massive star, a Type B main sequence star, shining blue-white with a brilliance tens of thousands of times greater than our Sun. It burns hot and fast, the kind of star that lives only a few million years compared to the billions our Sun will endure. But while its life may be short on a cosmic scale, it has achieved a kind of immortality in human history because of its role as a witness to one of the most extreme regions of the universe. In our minds, in our stories, and in the legacy of science, S2 has already transcended time. There's something profoundly poetic about S2's place in the cosmos. On one hand, it is completely ordinary in the sense that it is just another star, nuclear fusion roaring at its core, sending light into the darkness. On the other hand, it exists in an environment so extreme that it becomes extraordinary by default. If you placed our Sun where S2 resides, it would not last. The gravitational pull, the sheer energy of the environment, the stresses of the orbit would destabilize it. But S2 thrives there. It is as though it was born for this perilous dance. When astronomers call it the Immortal Star, they're not literally suggesting it can live forever. Stars, after all, have finite lives. What they mean is that S2 seems to embody resilience against impossible odds. Every time it swings near Sagittarius A, skimming the edge of what we would call certain death, it survives, unchanged, eternal in its cycle. To observers, it feels as though this star has a defiance about it, as though it refuses to bow to the monstrous darkness at the center of our galaxy. And so S2 is more than a scientific curiosity. It has become a symbol. To scientists, it represents one of the best tools for unlocking the mysteries of black holes. To storytellers, it represents bravery in the face of annihilation. To humanity as a whole, it is a reminder that even in the most hostile corners of the universe, beauty and persistence endure. Orbiting Sagittarius A in its precise, daring path, S2 is not just a star. It is a cosmic survivor, a messenger, a beacon from the very edge of spacetime. When we peer at it through our most powerful instruments, we are not merely studying a star, we are watching a drama unfold on the grandest of stages, where gravity and light perform a play written in the language of Einstein and carved into the very geometry of the universe. To truly appreciate S2, you have to let your mind wander into the realm of the extreme. This is not just another star twinkling serenely in the night. S2 is a star caught in a cosmic battlefield where the laws of physics are stretched, twisted, and tested in ways we can hardly imagine. Every orbit it completes is like a science experiment written in fire and gravity, a performance that reveals truths about the very structure of spacetime itself. Let's begin with the gravity. Sagittarius A doesn't merely pull, it warps reality. Its gravity is so immense that it literally reshapes the fabric of space around it. The closer S2 ventures to the black hole, the deeper it dives into this distorted landscape. The space through which the star moves is not the same space you and I experience here on Earth. It's bent, curved, sculpted by the overwhelming presence of a mass 4 million times greater than the Sun. To us, gravity makes apples fall from trees and keeps the Moon in orbit. But to S2, gravity is a cosmic titan, an ever-present force pressing down on it with unimaginable strength, pulling at it with relentless intensity, daring it to come just a little closer. And then there's the speed. When S2 swings near its closest approach to Sagittarius A, it doesn't just drift casually along. It rockets through space at over 7,600 kilometers every single second. To put that into perspective, in the time it takes you to blink, S2 has traveled farther than the entire diameter of Earth. This is about 3% of the speed of light, an almost absurd velocity for a star, a speed that dwarfs anything our minds are used to. Our planet, Earth, races around the Sun at about 30 kilometers per second, a pace that already feels dizzying when you stop to think about it. Yet S2 makes that look almost laughably slow. It is as though this star is in a cosmic drag race, one in which the stakes are nothing less than survival. But speed and gravity are only part of the story. What happens to S2 is even stranger than motion itself, because time, the very flow of existence, bends in the presence of such immense gravity. This is not science fiction, it is Einstein's general relativity at work. Near Sagittarius A, time does not pass the same way it does for you and me. For S2, moving through the warped spacetime near the black hole, time ticks ever so slightly differently. If we could somehow stand on a planet orbiting S2, looking back toward Earth, we would find that our clocks and theirs would fall out of sync. To them, time would feel normal, but to us, their moments would appear stretched, slowed, distorted by the immense gravitational field they are immersed in. This is what scientists call time dilation, and S2 experiences it in a way no human ever could. Even the light from S2 is touched by these extremes. As it races through the curved spacetime near the black hole, its light waves stretch and shift, a phenomenon known as gravitational redshift. That means when we observe S2 from Earth, its glow isn't quite the same as it would be in the calm of interstellar space. Instead, it carries the unmistakable fingerprint of the black hole's gravity. Each photon, each particle of light, is stretched as it claws its way out of the gravitational well, delivering to us not just illumination, but direct evidence of Einstein's predictions unfolding in real time. Think about this for a moment. We are not merely watching a star orbit a black hole. We are watching the very laws of nature being tested. We are seeing speed approach cosmic limits. We are witnessing time itself slow and light itself bend. S2 is like a living probe sent by the universe, tracing a path through conditions so extreme that our most advanced laboratories could never hope to reproduce them. This is the hook, the irresistible draw of S2's story. It's not just about a star orbiting a black hole, it's about what that orbit teaches us. It's about seeing relativity in action, about watching gravity bend reality, about realizing that the universe is stranger, wilder, and more awe-inspiring than our everyday experience could ever suggest. Every time S2 swings past the dark heart of Sagittarius A, it's as if the universe itself is offering us a demonstration. This is how spacetime works when pushed to the edge. When we speak of S2's orbit, we're not talking about a simple, serene path like the one Earth takes around the Sun. This is an orbit written in extremes, a cosmic ellipse stretched tight by the gravitational grip of Sagittarius A. And unlike our calm annual journey, S2's orbit is a long and dramatic pilgrimage that takes about 16 Earth years to complete. Think about what that means. In the time it takes a child to grow from birth to the brink of adulthood, S2 has circled the supermassive black hole just once. For us, 16 years feels like a long stretch of life. Presidents change, cities transform, whole generations of technology rise and fall. Yet on the galactic scale, 16 years is less than a heartbeat. It is a blink in cosmic time, so brief that astronomers alive today have been able to watch S2 complete full revolutions with their own eyes. This is a rarity in astronomy. Most stars and planets take thousands or even millions of years to complete their orbits around massive bodies. But S2's 16-year cycle puts it within reach of human observation, allowing us to track its entire journey in a single lifetime. The shape of this orbit is telling. It is not a circle, as one might imagine a star would carve if it was serenely revolving around a central mass. Instead, S2's orbit is highly elongated, stretched like an ellipse drawn by an invisible hand. This means that there are moments when the star is flung far out into the crowded stellar fields of the galactic center, and moments when it plunges terrifyingly close to the black hole itself. Each of these swings is like a dare, a near-death encounter where it skirts the very edge of destruction, only to whip back out again, propelled by the same gravity that nearly devours it. From our perspective on Earth, astronomers have painstakingly charted this orbit, watching S2 trace its path over decades. And every time it swings back toward its closest approach, the tension builds. Will the star survive another pass? Will the data it provides confirm our theories or shatter them? Each lap is a chapter in a long story written against the backdrop of Sagittarius A, a story that humans are privileged to witness only because the orbit is short enough for us to follow. The 16-year period also makes S2 a natural clock for the galactic center. Just as Earth's orbit defines a year for us, S2's orbit defines a kind of galactic heartbeat, a rhythm that astronomers have learned to rely on. With each completion, the data becomes richer, the measurements sharper, and our understanding of black hole physics more precise. Watching S2 orbit is like watching a pendulum swing in a laboratory, except this pendulum is the size of a star, and the laboratory is the warped spacetime of a supermassive black hole. And the drama of this orbit is magnified by how unforgiving it is. When S2 ventures close, it experiences the most extreme physics known to science. Gravity so strong it bends light, speeds that nearly rival the limits of the universe, and time dilation that subtly shifts its experience of reality. Then, as if nothing happened, it arcs back outward, retreating to a calmer distance, only to be drawn in once more. It is a cycle of risk and survival, repeated endlessly, as though the star has been fated to enact this dangerous dance for as long as it burns. Every 16 years, the universe gives us a front-row seat to this performance. We are reminded that while our own lives move in cycles of days and years, stars and black holes play out their dramas on scales both longer and shorter than we might expect. In S2, we find a rare alignment, a cycle short enough to track, yet powerful enough to reveal truths about the cosmos that would otherwise remain hidden. When S2 makes its daring dive toward the black hole at the heart of the Milky Way, the distance it closes into is almost inconceivably small by galactic standards. At its nearest approach, S2 comes within 17 light-hours of Sagittarius A. That number might sound abstract, so let's break it down. A light-hour is the distance light travels in 1 hour, nearly 1.08 billion kilometers. 17 of those is about 18 billion kilometers. To our everyday minds, that's an impossible distance to picture, but in the theater of the cosmos, it's unimaginably close. For comparison, Neptune, the farthest major planet in our solar system, orbits at about 4 light-hours from the Sun. That means when S2 skims past Sagittarius A, it is only about 4 times farther from the black hole than Neptune is from our Sun. But remember, Sagittarius A contains the mass of 4 million suns, crushed into a region smaller than our solar system. In other words, S2 is threading the needle around an abyss millions of times more massive than the star that sustains our lives, at a distance comparable to one of our outer planets. This is the astrophysical equivalent of brushing past a hurricane with the size of a galaxy, and somehow not being shredded to pieces. What makes this so extreme is that black holes are not gentle neighbors. Their gravity is not a friendly tether like the pull of Earth on the Moon. It is violent, relentless, and all-consuming. At 17 light-hours, the gravitational field is fierce enough to twist space itself into a funnel. If S2 came only a little closer, the forces would tear it apart in what astronomers call spaghettification, the stretching of matter into thin strands as tidal forces overwhelm its structure. Yet S2 holds steady, whipping past in a fiery streak, close enough for us to measure relativity in action but far enough to survive another loop. 17 light-hours is also small compared to the scale of the galactic center. The stars clustered their orbit at distances measured in light days, light weeks, or more. Most stars never dare venture anywhere near the black holes. More. S2 is an outlier, a daredevil. Its elliptical orbit drags it into a region where only the boldest stars go, into a space where human intuition says no star should exist. And yet, there it is, circling again and again, like a moth that flies so close to a flame that it should burn, but somehow doesn't. This proximity also makes S2 a goldmine for science. The closer it goes, the stronger the relativistic effects become, and the more clearly we can measure them. 17 light-hours may sound like a buffer of safety, but in physics, it's a razor's edge, close enough to be influenced by the black hole's most extreme gravity, but just far enough that we can study it without watching the star vanish forever. It's as though the universe has given us a perfect vantage point, a star that is brave enough, or perhaps unlucky enough, to wander within reach of the abyss without falling in. When astronomers describe this distance, they often remind us that it is extremely close on a galactic scale. And it truly is. The Milky Way is 100,000 light-years across. Light takes over 8 minutes just to reach Earth from the Sun. Yet S2 dares to approach the supermassive black hole to within a span of hours in light travel terms. If the galaxy were shrunk to the size of a city, S2 would be orbiting within a few centimeters of its central skyscraper, while everything else stayed blocks away. It's that precarious, that astonishing, and that improbable. Every time S2 reaches this point, its pericenter, the moment of closest approach, astronomers around the world focus their telescopes on the galactic center. It is the climax of the star's 16-year journey, the moment when the drama of its orbit is most intense. The data from these encounters have transformed our understanding of black holes, gravity, and relativity. And to think, all of it is made possible because a single star dares to pass within just 17 light-hours of a monster that could swallow millions of suns without hesitation. Speed, in the everyday world, is something we can wrap our minds around. A fast car might hit 300 kilometers per hour. A jet streaks through the sky at nearly 1,000 kilometers per hour. Even rockets leaving Earth for space travel manage a blistering 28,000 kilometers per hour to break free of our planet's gravity. These numbers feel huge to us, almost incomprehensible in their power. But when we turn our eyes to the Immortal Star S2, those speeds become child's play. At its closest approach to Sagittarius A, S2 hurtles through space at an astonishing 7,650 kilometers per second. That's not per hour, per second. Let's put that in perspective. That speed translates to roughly 27.5 million kilometers per hour. In just 1 second, S2 travels a distance greater than the diameter of Earth. In a single minute, it could circle our planet nearly 120 times. In an hour, it could travel from Earth to the Moon and back more than 40 times. Numbers like these are not just extreme, they're almost absurd. Astronomers often simplify it for us by saying S2 moves at about 3% the speed of light. Light, the fastest thing in the universe, sets the ultimate cosmic speed limit at about 300,000 kilometers per second. S2, a ball of nuclear fire not so different from countless stars in the galaxy, manages to push itself to nearly 1/30th of that absolute maximum. For a star bound by gravity, that's breathtaking. Very few stars anywhere in the universe have ever been clocked at such velocities. And it's no wonder. The only reason S2 can achieve this kind of speed is because it lives in the gravitational clutches of a monster. Sagittarius A is a cosmic slingshot, its immense gravity pulling S2 inward, accelerating it to velocities that defy our sense of what stars should be capable of. As the star approaches its pericenter, the point of closest approach, it's essentially surfing down a gravitational well, whipped around like a comet skimming past the sun, only magnified by factors of millions. When it reaches that blistering 7,650 kilometers per second, it's not just moving fast. It's moving in a regime where relativity takes hold, where time itself and the nature of light are altered by motion. It's worth pausing to compare this with our own planet's motion. Earth, orbiting at a comfortable distance from the Sun, travels around our star at about 30 kilometers per second. That already feels impossibly quick compared to our daily lives. Yet S2 is moving at more than 250 times that speed. Imagine every highway, every train, every jet, every spacecraft we've ever launched, all of them multiplied by hundreds, and you still wouldn't reach what S2 accomplishes effortlessly at each swing past the black hole. This is not motion in any human sense. It's motion on the edge of physics itself. At these speeds, the predictions of Einstein's relativity aren't just theoretical, they become necessary. Classical mechanics, the equations of Newton that describe the motion of most things we encounter, can't fully explain what's happening to S2. The faster it moves, the more its mass, light, and time are affected by relativistic effects. Its orbit becomes a laboratory, a rare stage upon which we see the strange but precise rules of relativity etched into reality. The speed also tells us something about the danger S2 faces. At 7,650 kilometers per second, a single miscalculation, a deviation in orbit, a fluctuation in mass, could spell doom. If S2 dipped just slightly closer, its speed would increase, the gravitational tides would intensify, and it might be pulled beyond the point of no return. It's living on a knife's edge, balanced between survival and destruction, with its velocity serving as both shield and potential downfall. From Earth, when astronomers measure this speed, it isn't just a curiosity. It is proof of the extraordinary gravitational pull of Sagittarius A. It is a cosmic certificate, stamped by physics itself, that only a black hole of millions of solar masses could fling a star to such velocities. Every time S2 blazes through its pericenter, it carries with it a signature, one that shouts to the cosmos, "Here lies a monster. Here lies a black hole beyond imagination." Here on Earth, we often forget that we, too, are in constant motion. Even as you sit still, listening to these words, our planet is racing around the Sun at a velocity of about 30 kilometers per second. That's more than 100,000 kilometers per hour, a speed so vast that in a single day, Earth covers more than 2.5 million kilometers of orbital path. We don't feel this motion because everything around us, air, oceans, land, and life itself, is carried along in the same cosmic ride. But make no mistake, we are all passengers on a planet moving faster than any human-made machine has ever traveled. Now, take that speed and compare it to what S2 achieves when it swings past Sagittarius A. Earth's 30 kilometers per second sounds staggering to us. But S2 moves at 7,650 kilometers per second, a speed more than 250 times faster than our planet's orbital pace. If Earth was suddenly thrown into S2's orbit around the black hole, our world would need to accelerate by that factor just to keep up. The difference is almost comical. It's like comparing the pace of a gentle jog to a rocket breaking the sound barrier 1,000 times over. To make it even clearer, in 1 second, Earth travels about 30 kilometers in its orbit, roughly the distance from one city to another nearby. In that same second, S2 streaks across 7,650 kilometers, a span that could take you from New York to Paris, then onward to Moscow, and still leave distance to spare. In the time it takes to blink, Earth has edged forward ever so slightly in its orbit, while S2 has leapt thousands of kilometers closer to or farther from its black hole companion. This contrast highlights the extraordinary nature of the galactic center. Our Sun, with its reassuring warmth and stability, doesn't demand much of its planets. Earth's speed is enough to balance the Sun's gravity at our comfortable distance. But Sagittarius A is a different kind of master. For S2 to survive in orbit around something so massive, it has to move at velocities that nearly defy comprehension. Slow down even a little, and the black hole's pull would drag it past the event horizon, never to return. It is speed itself that allows S2 to endure, speed that transforms the deadly gravity of Sagittarius A into a delicate balance of orbital motion. This comparison also reminds us of just how sheltered we are here in our solar system. Earth's orbit is stable, calm, and relatively uneventful. Year after year, we circle the Sun with little variation, following a gentle path in a cosmic neighborhood that is, by galactic standards, remarkably safe. Meanwhile, S2 exists in a far harsher reality, orbiting through a region where black holes lurk, stars collide, and gravity bends spacetime into strange shapes. Its velocity is not a luxury, it is survival. Yet the numbers don't just inspire awe, they serve as evidence. When astronomers measure S2's incredible speed and compare it to Earth's modest orbital pace, they are forced to reckon with what could possibly create such conditions. No star, no cluster, no hidden swarm of objects could account for it. Only a single, compact body with millions of solar masses, a supermassive black hole, could demand such an outrageous speed for orbital stability. In this way, the comparison between Earth and S2 isn't just a dramatic statistic, it's one of the strongest arguments for the very existence of Sagittarius A. So the next time you look up at the sky and consider the journey Earth is making around the Sun, remember that there is another star out there, deep in the heart of the Milky Way, that is living life at a completely different pace. While we orbit with gentle steadiness, S2 whips around its black hole master with a velocity that stretches the limits of imagination. Our world moves with grace, but S2 moves with fury, a cosmic racer in the ultimate track, its speed a testament to both the danger and the wonder of the galactic core. When most of us picture orbits, we imagine circles, neat, balanced paths where a planet or star gently glides around its central partner. That image comes from our everyday example, Earth's orbit around the Sun, which is almost perfectly circular. But S2's journey around Sagittarius A is nothing like that. Its path is not a calm loop but a stretched ellipse, an elongated oval carved into spacetime by the immense pull of the supermassive black hole. This elliptical orbit means that S2 spends much of its time far away from Sagittarius A, moving in broader, slower arcs, before plunging into a wild, death-defying sprint at its closest approach. Think of a comet in our solar system, like Halley's Comet, which drifts slowly through the outer reaches for decades before slingshotting past the Sun in a brilliant flash. S2 behaves much the same way, though on a far grander and more dangerous scale. At the farthest end of its orbit, known as the apocenter, S2 is more than 100 times farther from Sagittarius A than it is at its closest approach. Out there, its motion is calmer, and the gravitational grip of the black hole loosens slightly. But this tranquility is temporary. The black hole's invisible tether eventually reels it back in, pulling S2 into its pericenter, the closest point of its orbit, where all the drama happens. This elliptical swing, slow and wide at one end, fast and furious at the other, defines S2's life. The stretched shape of the orbit tells us something fundamental about the conditions in the galactic core. In classical mechanics, an object orbiting a central mass can trace out ellipses, circles, parabolas, or hyperbolas depending on its energy. A perfect circle would mean the object's speed and gravitational pull are in flawless balance. An ellipse, however, means the star's velocity varies. It speeds up when close and slows down when far away. In S2's case, the elongation of the ellipse is dramatic, almost extreme, proof of just how much the black hole's gravity dominates. But here's where it gets even more fascinating. S2's orbit is not a perfect ellipse, as Newton's laws would predict. Instead, it precesses, it shifts slightly with each cycle. When astronomers map its orbit over multiple passes, they see that the ellipse doesn't close neatly. Instead, The path rotates, forming a rosette pattern over time. This is not an error in observation but a direct effect of Einstein's general relativity. Spacetime near the black hole is curved so intensely that Newton's neat equations fall apart. The orbit's precession is exactly what relativity predicts, the same effect observed with Mercury around the Sun, but magnified here into a breathtaking demonstration on a cosmic stage. Imagine the orbit as a stretched rubber band pinned at one end. Over time, the band doesn't snap back into the exact same shape but shifts slightly, warping into new positions. That's what S2 does every 16 years. Each loop is different, not because the star is unstable, but because spacetime itself is warped and dynamic under the influence of Sagittarius A. For astronomers, watching this precession unfold is like reading a physics textbook written directly into the sky. It's confirmation, in motion, that Einstein's equations hold true even under some of the most extreme conditions in the universe. What's remarkable is how this orbit has become more than just a curiosity. It is a measuring stick. By tracing S2's elongated path, scientists can calculate not only the mass of the black hole but also the distribution of stars, gas, and dark matter in the galactic center. The orbit acts like a probe, sweeping out an invisible map of the forces shaping the core of the Milky Way. The precise way S2's ellipse shifts tells us about the unseen structure of the galaxy's heart. So when we talk about S2's orbit being an ellipse rather than a circle, it isn't just geometry. It's the very fingerprint of the black hole's presence, the curve of spacetime itself written into the path of a star. A circle would be ordinary. An ellipse is extraordinary. And a precessing ellipse, a shifting, rosette-shaped dance, is nothing less than a signature of relativity in action, unfolding 26,000 light-years away, but visible to the instruments we point toward the galactic core. S2's orbital path is a story in its own right, a star stretched and swung into a cosmic slingshot, looping again and again in a shape that reminds us of both the predictability and the strangeness of the universe. It is not just an orbit, it is a message carved into the night sky, telling us about the black hole it circles, about the laws of gravity that govern it, and about the very fabric of reality itself. Einstein's general theory of relativity is one of the crown jewels of human thought, a framework that reshaped how we understand gravity, space, and time. Instead of treating gravity as an invisible force pulling objects together, Einstein described it as the curvature of spacetime itself. Massive objects bend the fabric of the universe, and smaller objects simply follow those curves. Planets orbit stars not because they're tugged by some mysterious hand, but because they're tracing out paths in a warped landscape of spacetime. For over a century, relativity has been tested in countless ways. Light bending. During a solar eclipse, the precession of Mercury's orbit, the slowing of time on satellites in Earth's gravitational field. Every time, Einstein's equations have held true. But the ultimate test requires extremes, places where gravity isn't just strong, but overwhelming. And that's where S2 becomes indispensable. By daring to orbit so close to Sagittarius A, S2 plunges into a realm where relativity's predictions are pushed to their very limits. At its closest approach, the star moves at 3% of the speed of light and skims within just 17 light-hours of a black hole with 4 million solar masses. No laboratory on Earth could recreate such conditions, and no other known star in our galaxy has provided such a clear view of gravity in this regime. For scientists, S2 is a once-in-a-lifetime opportunity, a natural laboratory for testing Einstein's masterpiece against the universe's most unforgiving forces. One of relativity's most famous predictions is that orbits near massive objects don't behave like the neat ellipses predicted by Newton. Instead, they precess, the ellipse shifts slightly, so the star traces out a rosette pattern over time. This effect was famously observed with Mercury in our solar system, which doesn't return to the exact same orbit with each revolution around the Sun. But Mercury's precession is subtle, a tiny wobble. With S2, the effect is magnified thousands of times. Its elongated orbit visibly shifts with each 16-year cycle, and by tracking it, astronomers can watch relativity playing out before their eyes, like a live experiment in spacetime. Relativity also predicts that light escaping a strong gravitational field will lose energy, stretching into longer wavelengths, a phenomenon known as gravitational redshift. As S2 swoops toward the black hole, its light struggles to climb out of the steep gravitational well. From Earth, astronomers can measure this subtle shift, a fingerprint of gravity tugging on photons themselves. This isn't just theory, it has been observed directly in S2 spectrum. In 2018, during one of its closest passes, astronomers saw the star's light stretch in precisely the way Einstein said it would. It was a stunning confirmation, delivered from a star orbiting on the edge of spacetime. Another test lies in time dilation. According to relativity, time flows differently depending on how fast you're moving and how deep you are in a gravitational well. Near Sagittarius A, both factors come into play. S2's tremendous speed and its proximity to the black hole mean its clock ticks ever so slightly slower than ours. This difference is tiny but measurable, and it provides yet another way to probe relativity. By monitoring the timing of S2's orbit with incredible precision, astronomers can detect this distortion of time itself. Each of these phenomena, orbital precession, gravitational redshift, time dilation, has been predicted for over a century. But seeing them tested not in theory or in small-scale experiments, but in the wild, near a real black hole, is breathtaking. It's like watching the equations come alive. S2, without ever knowing it, has become a partner in one of humanity's greatest scientific endeavors, proving, again and again, that Einstein's vision of gravity was correct, even under conditions that strain our imagination. And yet, while relativity continues to triumph in these tests, scientists remain eager for more. Could there be subtle deviations, cracks in the equations that point toward new physics? S2's orbit is so precise, so extreme, that even the tiniest departure from Einstein's predictions could open the door to discoveries beyond relativity. Perhaps insights into quantum gravity, the long-sought bridge between the physics of the very large and the physics of the very small. That's why S2 isn't just fascinating, it's revolutionary. Each time it loops around Sagittarius A, it doesn't just survive the impossible. It delivers to us a set of data points, a living experiment in curved spacetime. And in doing so, it gives humanity the rare chance to stand at the edge of Einstein's theory, to test it where it has never been tested before, and to ask the question, is this truly the final word on gravity, or is there something more waiting to be discovered? When we talk about light from a star, we often imagine it as something pure and untouchable, racing across space unchanged until it reaches our eyes or our telescopes. But in the universe, light is not immune to the forces around it. One of the most striking demonstrations of this is the phenomenon of gravitational redshift, a direct prediction of Einstein's general relativity, and S2 gives us one of the clearest, most dramatic examples of it in action. Here's the idea in simple terms. When light climbs out of a gravitational field, it loses energy. And because light can't slow down, its speed is fixed by the laws of physics. The only way it can shed energy is by stretching its wavelength. Shorter wavelengths, like blue or ultraviolet, become longer, shifting toward the red part of the spectrum. This is why we call it redshift. In other words, light escaping a deep gravitational well emerges slightly redder than when it was emitted. Now, in everyday life, this effect is so tiny that we don't notice it. Light from your desk lamp, for instance, isn't being pulled hard enough by Earth's gravity to shift its color in any meaningful way. Even stars like our Sun produce only the faintest gravitational redshift, measurable only with extremely precise instruments. But when we turn our gaze to S2, orbiting so perilously close to Sagittarius A, the effect becomes impossible to ignore. As S2 plunges toward its pericenter, the point where it skims just 17 light-hours from the supermassive black hole, its photons must claw their way out of one of the steepest gravitational wells in our galaxy. Each particle of light struggles to escape, stretched thinner and thinner as it climbs away from the invisible monster at the galaxy's heart. By the time that light reaches Earth, it carries the unmistakable fingerprint of gravitational redshift. Its spectral lines shifted toward longer wavelengths compared to what we would expect if the star were in a weaker gravitational environment. Astronomers had anticipated this effect for decades, but observing it required extraordinary patience and technology. They had to track S2 over many years, waiting for one of its close approaches to the black hole, and then capture its light with instruments sensitive enough to detect the tiny changes in wavelength. The breakthrough finally came in 2018, when teams using the European Southern Observatory's Very Large Telescope observed S2 spectrum as it swept past Sagittarius A. There, in the data, was the shift, exactly as Einstein's theory predicted a century earlier. It was a historic moment. For the first time, scientists weren't just reading about gravitational redshift in equations or inferring it from faint hints. They were watching it unfold in real time, from a star orbiting the very edge of spacetime. It was as if the universe itself had raised a hand and said, "Yes, relativity is real. This is how gravity shapes light." What makes this even more profound is how it ties into our perception of reality. The redshift isn't just a neat trick of physics, it's a direct sign that time and energy themselves are altered by gravity. To us on Earth, far from the black hole, S2's light appears stretched and delayed. But to the star itself, nothing seems different. Its photons leave at their usual energy. It's the warped spacetime between S2 and us that distorts them, bending not only their paths but also their very frequency. We are, in essence, peering at light that has been filtered through the curved fabric of the universe. This phenomenon also connects to the larger puzzle of how we measure the universe. Astronomers regularly use redshift to calculate how fast galaxies are moving away from us, a cornerstone of our understanding of cosmic expansion. But what S2 shows is that redshift doesn't always mean motion. Sometimes, it's gravity itself stretching light, showing us the invisible hand of mass bending spacetime. This distinction is critical, because it proves that the very same effect shaping the largest scales of the universe can also be seen in the intimate dance of a single star and a black hole. The gravitational redshift observed from S2 wasn't just a triumph of relativity, it was a triumph of human ingenuity. It demonstrated that, across 26,000 light-years, we could measure a shift in the light of a single star caused by the invisible pull of a black hole. It's almost poetic. The faint shimmer of a star becomes a messenger, carrying across the galaxy a direct signal of the laws that govern reality itself. And what's perhaps most humbling is that this is not a rare, one-time event. Each time S2 loops through its orbit, each time it approaches the black hole and then swings back out, it will show us this redshift again. It's as if the universe has gifted us a repeating experiment, a cosmic metronome marking the rhythm of spacetime, allowing us to test and retest our deepest theories again and again. Time is something we usually take for granted. We measure it with clocks, we feel it in heartbeats, and we live it in days and years. To us, it feels universal, an unstoppable river flowing at the same pace everywhere. But Einstein shattered that illusion. His theory of relativity showed that time is not absolute. It stretches, compresses, and bends depending on two key things: speed and gravity. And S2, living on the edge of a supermassive black hole, is one of the clearest demonstrations of this truth. Let's break it down. First, consider speed. According to Einstein's special relativity, the faster you move, the slower time flows for you compared to someone standing still. This isn't science fiction. It's been proven many times. Astronauts aboard the International Space Station, traveling at 28,000 kilometers per hour, actually age slightly less than people on Earth. The difference is tiny, just milliseconds, but it's real. Now, take that effect and multiply it by S2's insane velocity, 7,650 kilometers per second, about 3% the speed of light. At that speed, time for S2 ticks measurably slower than it does for us back on Earth. But velocity is only half the story. The other half is gravity. General relativity predicts that time runs slower in stronger gravitational fields. Imagine spacetime as a stretched sheet. A massive object like Earth makes only a shallow dent, but a supermassive black hole makes a nearly bottomless pit. The closer you get to that pit, the more time itself slows down. S2, swooping in just 17 light-hours from Sagittarius A, skims along the edges of this abyss. To the star itself, everything seems normal. Its nuclear reactions burn steadily, its atoms vibrate as they always have. But from our vantage point, far away in a weaker gravitational field, S2's time is distorted. It is literally ticking slower than our own. This effect, called gravitational time dilation, is not just theory, it has been measured. In 2018, when astronomers carefully tracked S2 during its closest pass to the black hole, they combined observations of its speed with the gravitational redshift of its light. The results matched Einstein's predictions perfectly. Both velocity and gravity were warping time around S2. To us, its clock was running behind, as if the star were moving through a thicker, heavier flow of time compared to our own. Think about the implications. Imagine that S2 had planets around it, with civilizations, living under its light. To them, a year would pass normally. Their clocks would tick, their lives would unfold at what they'd perceive as the natural rhythm. But from Earth, watching across 26,000 light-years, we'd see those same clocks running slower. If we could somehow exchange signals, we'd notice a discrepancy, a strange mismatch in the passage of time. Their now would not align perfectly with ours. This isn't just a thought experiment, it's how the universe actually works. Time itself, the very medium in which we live our lives, is flexible, shaped by gravity and motion. And this is what makes S2 so extraordinary. It's not just orbiting a black hole, it's showing us, in real time, how relativity governs the flow of existence. Each orbit becomes a cosmic experiment, with the star's time stretched and skewed compared to our own. By measuring this, astronomers can confirm predictions made over 100 years ago, predictions that sound almost mystical yet are proven by physics again and again. What's more, this isn't just academic curiosity. Gravitational time dilation is woven into the very technology we use every day. GPS satellites, orbiting Earth, experience time slightly differently than clocks on the ground, and without correcting for relativity, our navigation systems would quickly fail. S2 is simply the extreme version of that principle, showing us what happens when you crank up gravity and speed to galactic levels. So when we look at S2, we're not just seeing a star orbiting a black hole. We're seeing time itself being bent, twisted, and reshaped by the forces of the cosmos. To us, the Immortal Star is a messenger, whispering across the galaxy. Time is not fixed, it flows differently depending on where you are and how you move. That truth, hidden from our senses but revealed by relativity, makes S2 not just a star, but a teacher, one that shows us the universe is far stranger and far more beautiful than we ever imagined. When we look at the night sky, we take it for granted that the stars we see are exactly where they appear to be. We imagine that light travels in straight lines, darting from distant suns across the void until it enters our telescopes or our eyes. But in the deep truth revealed by Einstein's general relativity, light does not always travel straight. It bends when it passes near something incredibly massive, curving along the distorted fabric of spacetime. This effect, known as gravitational lensing, turns the universe into a hall of mirrors, where even the path of a photon can be twisted by gravity. Sagittarius A, the supermassive black hole at the center of our galaxy, is one of the most powerful examples of this. Its mass, 4 million times that of our Sun, warps spacetime so dramatically that anything passing nearby, even light itself, is forced to follow curved trajectories. And S2, orbiting in close proximity, allows us to see this phenomenon in action. When the star swings near its closest approach, the light it emits does not travel to us in a straight shot. Instead, it arcs subtly around the black hole, as if the very space between us and the star has been reshaped by the black hole's presence. This bending of light is not some vague idea, it's measurable. Astronomers have tracked the position of S2 with exquisite precision using advanced infrared instruments. And during its close passes, they have detected slight but unmistakable shifts in where the star appears to be. Shifts caused not by the star moving suddenly but by its light being redirected along curved spacetime. These tiny changes, just fractions of an arcsecond, are monumental in their significance. They show us, directly and undeniably, that light itself obeys Einstein's vision of gravity. To put this into perspective, the effect is similar to how glass lenses bend light on Earth, focusing it into an image on a camera or magnifying a text on a page. But, in this case, the lens is invisible. It's not a piece of glass but spacetime itself, warped by mass. The result is that the star's photons arrive at Earth after traveling along curved paths, slightly altering our view of where the star really is. The black hole becomes, in a sense, a cosmic lens through which we observe its companion. This bending isn't just a curiosity, it's a crucial tool. By measuring how light is deflected, astronomers can confirm the distribution of mass near Sagittarius A with extraordinary accuracy. The way S2's light is bent tells us not only about the black hole itself but also about the matter surrounding it. Stars, gas clouds, and perhaps even unseen concentrations of dark matter. Every photon from S2 carries information about the invisible landscape it traveled through before reaching us. What's more, this bending is a glimpse into the strange beauty of relativity. The idea that mass and gravity can twist light paths is counterintuitive. Light feels so intangible, so unyielding. Yet here, near S2 and the black hole, we see that even light must bow to gravity's command. The photons racing from S2 at 300,000 km per second cannot resist the warping of spacetime. They are forced to bend, and in bending, they reveal the shape of the universe itself. And the effects can be even more dramatic if conditions are right. If S2 were to align perfectly behind Sagittarius A from our perspective, the bending of its light could create what astronomers call an Einstein ring, a perfect circle of light around the black hole. While we haven't yet seen such a dramatic alignment with S2, the potential remains, and the principle is the same. The black hole doesn't just devour, it also distorts, magnifies, and reshapes the very light of the stars that dare to orbit it. To appreciate this, imagine standing on a hypothetical planet near S2. In your sky, the black hole would not simply appear as a void, it would act like a funhouse mirror. The stars around it would appear stretched, bent, and multiplied by the gravitational lensing effect. The view would be surreal, a reminder that what you see is not always what exists, and that spacetime itself can trick your eyes. So as S2 speeds through its orbit, it doesn't just show us how stars behave near a black hole. It shows us how light itself behaves, how even the purest messenger in the cosmos is bent and reshaped by gravity. These subtle deflections, measured across decades of careful observation, confirm yet again that Einstein's theory remains unbroken. In the dance of S2 and Sagittarius A, we see the bending of light as more than a phenomenon. We see it as proof that the universe is not a rigid stage, but a flexible, dynamic fabric where mass and light play together in ways both humbling and awe-inspiring. S2 is not just another star tucked into the crowded heart of the Milky Way. It is, in essence, a natural laboratory, the kind of cosmic experiment that humanity could never design on its own. Scientists often struggle to study black holes because, by their very nature, they do not emit light. You cannot see them directly with ordinary telescopes. Their presence is inferred from their influence on surrounding matter, gas, dust, and stars. And S2, orbiting so perilously close to Sagittarius A, provides one of the clearest and most reliable indicators of what's happening in this otherwise invisible realm. Every pass of S2 delivers a torrent of data about the black hole's gravitational pull. By tracking its motion, astronomers can calculate the exact mass of Sagittarius A, confirm that it is concentrated in an extraordinarily compact region, and rule out alternative explanations such as dense clusters of dark stars. In short, the star acts as a test particle in a gravitational field that is millions of times stronger than anything in our solar system, allowing physicists to study the black hole in a way no laboratory could replicate. Moreover, S2 allows researchers to examine general relativity in extreme conditions. Near the black hole, the fabric of spacetime is so warped that the classic Newtonian equations of motion fail to describe S2's path with perfect accuracy. Only Einstein's theory accounts for the slight precession of its orbit, the bending of light, and the gravitational redshift observed during its closest approaches. This makes S2 a rare, naturally occurring experiment in one of the universe's most extreme environments. A place where gravity is not gentle but overwhelming, yet measurable and predictable. Its high speed, its close proximity, and the clarity with which we can observe it all combine to create a perfect scenario for testing theoretical physics. S2 is like a cosmic particle accelerator without the infrastructure, without the walls or cost, stretching our understanding of the universe simply through its motion. Scientists have been able to use it to confirm that time does indeed dilate in the presence of immense gravity, that light bends as it travels through warped spacetime, and that the predictions of general relativity hold true under conditions far more extreme than anything on Earth. S2's scientific significance also extends beyond theory into the realm of practical measurement. Its repeated orbits allow astronomers to map the geometry of the galactic center with unprecedented precision. By tracking the star over decades, scientists can chart the invisible structure of the region, estimating not only the black hole's mass but also the distribution of other stars, gas clouds, and potential dark matter. It is like sending a tiny probe into a dark room and using its movement to map every corner and obstacle without ever seeing the room directly. Furthermore, S2's role is invaluable for predictive astronomy. Because its orbit is well understood, scientists can anticipate exactly where it will be at future times, allowing them to plan observations that test the limits of physics. Every close approach, every swing past the black hole, is an opportunity to refine models, measure relativistic effects with greater accuracy, and perhaps even detect deviations that hint at new physics. In essence, S2 is both a tool and a teacher, constantly offering new lessons in the mechanics of extreme gravity. The star's significance is not limited to testing known theories. It also helps scientists explore the unknown. For instance, by observing its orbit, researchers can look for subtle anomalies that could indicate the presence of additional massive objects, unseen companions, or unexpected gravitational influences. In doing so, S2 becomes a sentinel for uncovering hidden structure in the galaxy's core. The insights we gain are not just academic. They fundamentally shape our understanding of how galaxies evolve, how black holes influence their surroundings, and how gravity operates on the grandest scales. In short, S2 is the ultimate natural laboratory. Unlike anything we can replicate on Earth, it delivers real-world tests of extreme physics on a scale and under conditions that are impossible to recreate. Its orbit provides continuous, measurable, and repeatable experiments on the edge of a supermassive black hole, giving humanity a front-row seat to the most powerful forces in the universe. By studying S2, scientists are not only confirming theories, they are pushing the boundaries of what we know about space, time, and the cosmic dance of gravity itself. The story of S2's discovery begins in the late 20th century, in a period when astronomers were beginning to peer into the very heart of the Milky Way with unprecedented clarity. The center of our galaxy is cloaked behind vast clouds of gas and dust, making it invisible to optical telescopes. For centuries, this region was a mystery, a dark and silent void, punctuated only by occasional hints of stars and stellar activity through indirect observations. It wasn't until the advent of powerful infrared technology that scientists could start to penetrate these murky veils and glimpse the hidden stars orbiting the unseen core. In the early 1990s, a group of astronomers set out on an ambitious project to track the motion of individual stars near the galactic center over extended periods. Among these stars, one in particular drew attention. It was later designated S2, a luminous star tracing a dramatic and tight orbit around an unseen gravitational source. Early observations hinted that this star moved unusually fast, much faster than stars farther out from the center, and followed a highly elongated path. It was immediately clear that whatever S2 was orbiting, it had to be extraordinarily massive and compact. These observations were painstaking. Telescopes could not simply capture S2 in a single snapshot. The star's orbit spans decades, and its apparent motion across the sky is subtle. Astronomers had to compile years of data, carefully measuring the star's position against a backdrop of other stars and cosmic features. Each measurement brought new clarity. S2 was racing through space at velocities unimaginable for a star in a normal stellar environment, and its orbit was far too tight to be explained by ordinary matter. The realization that S2 was orbiting a supermassive black hole began to take shape in the mid-1990s. Teams led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics in Germany and Andrea Ghez in the United States were independently monitoring S2 and its stellar neighbors. Both teams noticed that S2's motion could only be explained by the presence of a single, incredibly dense, and invisible object, what we now know as Sagittarius A. The evidence was compelling. A star moving at thousands of kilometers per second along a highly elliptical orbit, repeatedly swooping perilously close to an unseen mass, then retreating again. By the late 1990s, S2 had become a key player in the debate over the Milky Way's central black hole. Its orbit offered a tangible way to measure the black hole's mass and test fundamental physics. Over the course of a few years, as more observations accumulated, astronomers could calculate its orbit with increasing precision, confirming both the extreme mass of the black hole and the remarkably short orbital period of just 16 years. This rapid orbit was unusual enough that S2 became a sort of poster child for studies of the galactic center, a star whose movements were impossible to ignore. It is remarkable to consider that, although the black hole itself is invisible, a single star like S2 could serve as a beacon, revealing its presence. The discovery process was not instantaneous. It was a slow, deliberate accumulation of evidence, spanning years of careful observation. Each new data point brought the story into sharper focus, and with each passing orbit, the reality became undeniable. A star was orbiting something unimaginably massive, providing the most direct evidence yet for a supermassive black hole at the center of our galaxy. This historical chapter is more than just a timeline. It represents a revolution in observational astronomy. The techniques used to track S2, the patience required, and the ingenuity in interpreting the data all highlight how extraordinary discoveries in astrophysics often emerge from persistence, precision, and a willingness to look where others cannot. In many ways, S2 was the first star to open a window into the hidden, high-energy world of the galactic center, a window that continues to provide revelations today. Observing S2 and the other stars near the Milky Way center is no simple feat. The galactic core lies about 26,000 light-years away from us, buried behind dense clouds of interstellar dust and gas that block visible light. Attempting to study it with ordinary optical telescopes is like trying to see a firefly through a foggy window from miles away. To overcome this barrier, astronomers turn to a combination of advanced infrared technology, adaptive optics, and powerful telescopes, creating tools capable of peering through the obscuring dust and capturing the movements of stars with astonishing precision. Infrared light is the key. Unlike visible light, which is heavily absorbed and scattered by dust, infrared wavelengths can pass through these clouds with relative ease. This allows telescopes to see stars in the otherwise hidden galactic center, including S2, in sharp detail. In the 1990s, when tracking of S2 first began, infrared cameras mounted on large ground-based telescopes enabled astronomers to detect individual stars orbiting around Sagittarius A. These instruments converted faint infrared signals into measurable data, revealing both the position and motion of S2 over time. Without infrared capabilities, S2's orbit would have remained entirely invisible. But simply detecting infrared light is not enough. The atmosphere of Earth distorts incoming light, causing stars to twinkle and blur in telescopes. To overcome this, astronomers employed adaptive optics, a revolutionary technology that uses deformable mirrors to compensate for atmospheric turbulence in real time. By adjusting the mirror's shape hundreds of times per second, adaptive optics sharpens images of distant stars, allowing scientists to pinpoint S2's position with incredible accuracy. These systems turned ground-based telescopes into instruments capable of rivaling the clarity of space-based observatories. Two of the most notable facilities in observing S2 are the Very Large Telescope, VLT, in Chile, operated by the European Southern Observatory, and the Keck Observatory in Hawaii. Both are equipped with cutting-edge infrared cameras and adaptive optic systems. The VLT, for example, combines four 8.2-meter telescopes, each capable of collecting enormous amounts of light, allowing astronomers to track faint stars in the galactic center over long periods. Similarly, Keck's twin 10-meter telescopes have produced some of the most detailed images and measurements of S2's orbit, helping to refine models of its motion and test predictions of general relativity. Spectroscopy is another vital tool. By splitting S2's light into its component wavelengths, astronomers can measure tiny shifts caused by the star's motion and the black hole's gravitational influence. These measurements reveal radial velocity, the speed at which S2 moves toward or away from Earth, which is critical for determining its orbit with precision. Infrared spectrographs, like those mounted on VLT and Keck, detect subtle Doppler shifts in the star's light caused by its extreme velocity and gravitational redshift near the black hole. This combination of imaging and spectroscopy has allowed scientists to map S2's orbit down to extraordinary detail, confirming both the mass of Sagittarius A and the relativistic effects on the star. The technological challenge doesn't stop at seeing through dust or measuring light shifts. Observing the galactic center requires decades of consistent monitoring. S2's orbit is 16 years long, so to capture an entire cycle and understand its dynamics, astronomers needed stable, reliable instruments that could deliver high-quality data year after year. This required not just hardware but also sophisticated software to analyze images, track motions over time, and correct for subtle distortions in the data. Advanced astrometric techniques allow researchers to measure S2's position to fractions of a milliarcsecond, a precision equivalent to spotting a coin on the surface of the Moon from Earth. Space telescopes like the Hubble Space Telescope and, more recently, the James Webb Space Telescope also complement ground-based observations. Freed from atmospheric interference, these instruments provide infrared observations of unprecedented clarity, giving astronomers yet another lens to confirm and refine ground-based data. In combination, these technologies create a multifaceted, high-precision observational platform, capable of revealing the complex dance of S2 around Sagittarius A with remarkable fidelity. Without these advancements in infrared imaging, adaptive optics, large telescope mirrors, and precise spectroscopy, S2's orbit would have remained a mystery. It is thanks to this technology that we can witness the closest star to the Milky Way's black hole, measure its speed, observe relativistic effects, and test the limits of Einstein's theory. In essence, S2 would exist in the darkness for us if it weren't for these instruments, and the story of the Immortal Star would be lost to the dust and shadows at the galaxy's heart. The year 2002 marked a defining moment in the study of S2 and the mysterious heart of the Milky Way. By then, astronomers had been tracking S2 for nearly a decade, mapping its orbit with painstaking care and marveling at its incredible velocity and proximity to Sagittarius A. But nothing would compare to the significance of its closest approach that year, an event that became a breakthrough for testing fundamental physics in ways never before possible. In 2002, S2 swung past Sagittarius A at a distance of just 17 light-hours, the pericenter of its orbit. At that moment, the star was traveling at an astonishing 7,650 kilometers per second, racing along the extreme curvature of spacetime created by the black hole. The close pass was more than just a thrilling astronomical event. It was the first opportunity for scientists to observe general relativity in action near a supermassive black hole. This was the moment when decades of careful observation, technological innovation, and theoretical work converged into a single, historic experiment. The 2002 pericenter pass allowed astronomers to measure gravitational redshift for the first time in a star so close to a black hole. As S2 swooped inward, its light was stretched by the immense gravitational field, shifting toward the red end of the spectrum. Using the infrared spectrographs on the Very Large Telescope and the Keck Observatory, researchers recorded subtle changes in the star's spectral lines. These shifts matched the predictions of Einstein's theory almost perfectly, providing a striking confirmation of relativistic effects at work in a regime far stronger than anything previously observed. At the same time, S2's extreme velocity during the pass offered a rare test of special relativity. The star's motion alone should cause measurable relativistic effects, including time dilation, where time runs slightly slower for S2 than for observers on Earth. Combined with the gravitational effects, this pass created a natural laboratory where both of Einstein's major contributions to our understanding of spacetime could be studied simultaneously. The 2002 event effectively transformed S2 from a curiosity into a cornerstone of modern astrophysics. The breakthrough didn't stop with relativistic confirmations. By precisely measuring the star's position during its pericenter, astronomers could refine calculations of Sagittarius A's mass with unprecedented accuracy. The data confirmed that the black hole contained about 4 million times the mass of the Sun, packed into a volume smaller than our solar system, a fact impossible to reconcile with any object other than a supermassive black hole. In this sense, S2's 2002 pass was not just a test of physics. It was a definitive proof that a gargantuan, invisible object dominates the heart of our galaxy. Beyond the numbers, the event had profound implications for observational techniques. The pericenter pass forced astronomers to push the limits of infrared adaptive optics, spectroscopy, and astrometry, demonstrating that they could measure positions and velocities with incredible precision even in one of the most challenging regions of the sky. Every data point gathered during this pass added confidence to models of S2's orbit, the structure of the galactic center, and the very methods by which we study extreme gravitational environments. The 2002 close approach also captured the imagination of the scientific community and the public alike. S2 had completed its closest swing around the black hole without being torn apart, surviving the violent gravitational forces that would destroy lesser stars. Its journey became a dramatic demonstration of the cosmic balance between speed and gravity, an illustration of the extreme physics playing out quietly 26,000 light-years away. The event marked the first time astronomers had a clear, direct view of a star navigating the warped spacetime near a supermassive black hole, a situation previously relegated to equations, simulations, and theoretical speculation. In short, the 2002 pericenter of S2 was not merely an observational milestone, it was a watershed moment in astrophysics. It confirmed that we could see Einstein's relativity at work on a galactic scale, measure the mass and influence of Sagittarius A with unprecedented precision, and track the orbital dance of a star under extreme gravitational stress. S2 had, for the first time, allowed humanity to test the deepest laws of physics in one of the most extreme environments in the universe. It was a breakthrough that transformed a distant star into one of the most important natural laboratories in modern science. The story of S2 does not end with a single dramatic pass. In fact, its true value comes from long-term observation, a patient and meticulous process that has spanned decades. Astronomers quickly realized that to truly understand this immortal star and the invisible giant it orbits, they needed to track S2 continuously, over multiple orbits, across years and even generations of telescopes. This long-term tracking has allowed them to build models of astonishing precision, revealing not only the star's orbit but also the subtle fingerprints of extreme physics at play. From the first infrared observations in the early 1990s, teams at the Very Large Telescope in Chile and the Keck Observatory in Hawaii began carefully charting S2's position against the backdrop of the galactic center. Each year brought new data points, tiny shifts in the star's position on the sky, minuscule changes in its velocity, and slight variations in brightness as it passed through different gravitational conditions. Every measurement, no matter how small, contributed to a growing picture of the star's motion. Tracking S2 is far from straightforward. The galactic center is crowded with thousands of stars, many of which move as well, creating a complex and shifting field. Atmospheric turbulence, interstellar dust, and instrument limitations all conspire to blur observations. But with adaptive optics, infrared imaging, and sophisticated data processing, astronomers have been able to disentangle S2 from the surrounding stars and trace its path with milliarc-second accuracy, a level of precision equivalent to spotting a coin on the surface of the Moon from Earth. Over the decades, these observations have allowed astronomers to construct a highly precise model of S2's orbit, capturing not only its elongated ellipse but also the subtle precession caused by the curvature of spacetime. With each successive orbit, the model becomes more refined. Scientists can predict S2's position years in advance and use it to test predictions from general relativity, including gravitational redshift, time dilation, and light bending. The long-term data also help confirm the mass of Sagittarius A with remarkable confidence, ruling out alternative explanations such as clusters of dark stars or other exotic matter. The persistence of these observations has paid off in unexpected ways. By comparing the star's positions over decades, astronomers have detected small deviations in its motion caused by the gravitational influence of other nearby stars, gas clouds, and possibly even dark matter. These subtle perturbations act like tracers of the galactic environment, providing clues about the otherwise invisible structure of the Milky Way's core. S2 is not merely a test of relativity, it is a probe into the broader dynamics of the dense, energetic region surrounding a supermassive black hole. Long-term tracking has also been essential for preparing for future passes. S2 completes its orbit roughly every 16 years, meaning astronomers need to anticipate when it will reach Center in order to schedule intensive observations. Planning for these moments involves careful analysis of decades of data, simulations of its orbit, and predictions of its velocity and position with incredible precision. This foresight allows telescopes to be ready when the star reaches its closest approach, ensuring that we capture every bit of information about gravitational effects, velocity shifts, and light distortions. The dedication required to follow S2 for decades highlights the extraordinary patience and foresight of the astronomical community. It is a long game. Each year, each observation, each tiny improvement in measurement techniques adds to a cumulative understanding that grows richer over time. By now, astronomers have witnessed more than a full orbit of S2, giving them the ability to compare its current motion with past predictions and test the consistency of physics over a human lifetime. In essence, S2 has become a living chronicle of the Milky Way's heart, a star whose repeated journeys provide a continuous stream of data that cannot be replicated in laboratories or simulated perfectly by computers. Its decades-long observation has transformed it into one of the most precise natural laboratories in existence, allowing scientists to refine our understanding of gravity, spacetime, and the invisible forces shaping the galaxy. Through long-term tracking, S2 has evolved from a distant point of light into a cornerstone of astrophysical research, a star whose every movement is measured, every Center passage anticipated, and every relativistic effect recorded with extraordinary care. This patience and persistence are why we now know not only that a supermassive black hole exists at the center of the Milky Way, but also how it bends spacetime, influences stellar motion, and shapes the cosmic environment in ways that continue to fascinate and challenge our understanding of the universe. The true significance of S2's orbit lies in what it reveals about the hidden powerhouse at the center of our galaxy. Before the careful tracking of this star, the existence of a supermassive black hole in the Milky Way was widely suspected but not directly proven. The dense core of stars, gas, and dust hinted at something extraordinary, yet the evidence was circumstantial. S2 changed that. Its orbital behavior provides some of the clearest and most direct proof of a supermassive black hole anywhere in the universe. S2's orbit is extreme in both speed and proximity. At its closest approach, the star skims just 17 light-hours from Sagittarius A, moving at roughly 7,650 km per second, about 3% the speed of light. For any object to maintain such a tight, high-speed orbit without being flung into space, there must be an enormous gravitational mass concentrated in a very small volume. Ordinary matter, such as a cluster of stars or a dense gas cloud, could never exert such gravitational influence without becoming unstable or observable through emitted radiation. Only a supermassive black hole, an object so dense that not even light can escape from its core, could anchor S2 in its perilous path. By precisely measuring S2's motion over decades, astronomers could apply Kepler's laws of orbital motion, combined with relativistic corrections, to calculate the mass of the central object. The result was staggering. Sagittarius A contains about 4 million times the mass of the Sun, concentrated within a region smaller than the orbit of Mercury. There is simply no alternative explanation. Any cluster of stars dense enough to produce the same gravitational effect would collapse, shine brightly, or interact violently. The only viable solution is a supermassive black hole, invisible yet omnipresent, holding S2 in a precise orbital dance. S2's elliptical orbit further reinforces this conclusion. The extreme elongation and the regularity of its path match what we would expect from a star orbiting a single, incredibly massive, and extremely compact object. If multiple masses were influencing S2, its motion would be chaotic, its path irregular, and the timing of its pericenter passage unpredictable. Instead, S2 traces a remarkably stable orbit, curving in a way that is consistent with both Newtonian mechanics on a large scale and Einsteinian general relativity near the black hole's gravitational well. This stability, combined with the sheer mass required, leaves no room for doubt. The 2002 pericenter passage and subsequent close approaches of S2 provided even more definitive proof. Observations of its velocity, light bending, and gravitational redshift all match predictions for a star orbiting a single supermassive black hole. Every spectroscopic measurement confirms the presence of a deep gravitational well that could be nothing else. It's as if S2 has been circling the black hole, silently confirming its existence, while we, millennia away, finally read the evidence encoded in the star's motion and light. Beyond the numbers, S2's orbit is visually compelling. The star's path, mapped over decades, forms a tight, elongated ellipse that points directly to the location of Sagittarius A. By tracing this ellipse backward and forward, astronomers can identify the precise position of the central mass, even though it emits no light itself. In essence, S2 acts as a cosmic pointer, circling a dark object whose gravitational influence is undeniable. Without S2, the black hole's location might remain hidden, a mystery obscured by dust and distance. In addition, the observation of S2 confirms the compactness of the black hole. The fact that a single star can orbit so close without being torn apart implies that the mass is confined to an incredibly small region. This is a hallmark of black holes: enormous mass in a tiny volume. S2's orbit rules out less exotic alternatives such as dense clusters of stellar remnants or intermediate mass objects, because such clusters would disperse or collide over time, disrupting the orbit. S2, in its fearless passage, validates the very definition of a supermassive black hole. Finally, the long-term tracking of S2 allows astronomers to predict future orbits with extraordinary precision. Each predicted position that matches observation reinforces the model of a central black hole. It is not a one-time observation but a repeated verification. S2 has become the ultimate witness. Its survival and precise motion testify to the reality of the invisible yet dominant gravitational force at the Milky Way's core. In short, S2's orbit doesn't just suggest the presence of a supermassive black hole, it proves it beyond reasonable doubt. Every swing past Sagittarius A, every high-speed dash near its pericenter, and every measurement of light and position confirm that a compact, powerful, and unseen mass rules the galactic center. Through S2, we see the invisible made undeniable, and the cosmic truth emerges. At the heart of our galaxy lies a supermassive black hole, and S2 is its tireless companion, orbiting as a living, moving testament to one of the universe's most profound phenomena. S2 does more than prove the existence of a supermassive black hole. It serves as a guide to the invisible architecture of the galactic center. The core of the Milky Way is a chaotic environment, densely packed with stars, gas clouds, and dark matter. This region is cloaked by thick interstellar dust, making it nearly impossible to see in visible light. S2, orbiting so close to Sagittarius A, acts like a celestial probe, helping astronomers map this hidden landscape and revealing the structure and dynamics of the heart of our galaxy. By tracking the precise motion of S2 over decades, scientists can determine not only the location and mass of the black hole but also the distribution of other objects in its vicinity. Stars near the galactic center are influenced by the gravitational pull of both Sagittarius A and each other, creating a complex gravitational field. Observing S2 allows astronomers to model this field with remarkable accuracy. Deviations in its orbit, however tiny, can signal the presence of other masses, like clusters of stars or concentrations of dark matter, that would otherwise remain invisible. The elongated orbit of S2 is particularly useful in this mapping process. Its repeated passages through the core, combined with the precision of modern infrared instruments, allow scientists to sample different regions of the galactic gravitational environment. Essentially, S2 sweeps out a path that probes the contours of spacetime around the black hole, acting like a cosmic test particle whose trajectory responds to every nearby mass. By analyzing these trajectories, researchers can construct a three-dimensional map of the galactic center's gravitational landscape. Moreover, S2's orbit provides a stable reference point for measuring the motions of other stars near Sagittarius A. By knowing exactly how S2 moves and where it should be at any given time, astronomers can calibrate their observations of fainter, less well-known stars. This calibration is crucial because the galactic center is so crowded that distinguishing individual stars is challenging. With S2 as a benchmark, the positions and velocities of hundreds of surrounding stars can be mapped with unprecedented accuracy, revealing clusters, streams, and patterns that illuminate the overall structure of the core. Another key insight comes from the interplay of S2's orbit and the gravitational effects predicted by general relativity. The star's motion is affected not only by the mass of Sagittarius A, but also by relativistic effects like orbital precession and gravitational redshift. By modeling these influences precisely, scientists can correct for distortions in observed positions and velocities, producing an even more accurate map of the galactic center. In effect, S2 acts as both a probe and a ruler, measuring the contours of the invisible landscape shaped by gravity and relativity. Studying S2 also sheds light on the distribution of dark matter near the galactic core. While dark matter cannot be seen directly, its gravitational influence affects the motion of visible stars. By comparing the predicted orbit of S2 based solely on the black hole's mass with the observed orbit, astronomers can infer the presence, or absence, of additional mass. So far, S2's path aligns closely with expectations, suggesting that the central region is dominated by the black hole, but continued tracking may reveal subtle discrepancies that point to hidden components of the galaxy's mass distribution. In addition to mapping mass, S2 helps reveal the dynamics of the galactic core. The velocities and accelerations of nearby stars, when analyzed in conjunction with S2's orbit, provide insight into how stars interact, how they migrate, and how the black hole's immense gravitational influence shapes the local stellar population. This has implications for understanding star formation, the evolution of stellar orbits, and even the processes that drive matter into the black hole over millions of years. S2's repeated, predictable passages give astronomers a living framework for charting the galactic center. Each orbit refines models of the core's structure, confirming the mass and position of Sagittarius A, revealing stellar clusters, constraining the distribution of dark matter, and providing a dynamic map of the environment around the galaxy's heart. It is like sending a probe into a dense, fog-shrouded city and using its movements to chart every street, building, and alley without ever leaving the edge of the fog. Ultimately, S2 is more than a star orbiting a black hole. It is a cosmic cartographer. Its fearless journey around the supermassive black hole illuminates the otherwise invisible structures of the galactic core, providing a guide that helps humanity understand the hidden heart of our galaxy. By studying S2, we not only confirm the black hole's presence but also gain a detailed map of the dense, complex, and dynamic environment surrounding it, a map that continues to evolve with every orbit. S2 is not only a proof of a supermassive black hole's existence, it is also a critical tool for testing and refining fundamental physics. While Einstein's general theory of relativity has withstood over a century of scrutiny, most experimental confirmations have occurred in relatively weak gravitational fields, on Earth, around the Sun, or in laboratory conditions. The extreme environment of the galactic center, where S2 races at thousands of kilometers per second close to a black hole containing millions of solar masses, provides a laboratory of gravity unlike any on Earth. Here, relativistic effects are magnified, and even subtle deviations from Einstein's predictions could reveal new physics. S2's orbit offers several avenues to test relativity. First, the precession of its orbital ellipse, the slow rotation of the ellipse over time, can be measured with high precision. While Newtonian mechanics predicts a closed elliptical orbit, general relativity predicts a slight forward rotation of the pericenter each orbit, caused by spacetime curvature around the black hole. Observing this precession in S2 confirms Einstein's equations in a regime of extreme gravity. However, any discrepancy, even small, could suggest additional phenomena, such as the influence of dark matter near the black hole or modifications to gravity at short distances. S2's data therefore serve as a probe into the limits of our current understanding. Another key test comes from gravitational redshift. As S2 approaches Sagittarius A, its light is stretched due to the intense gravitational field. The exact amount of redshift depends on the precise nature of the gravitational potential. Observations from the 2018 pericenter confirmed the predicted redshift with remarkable accuracy, but repeated observations refine these measurements further. With higher precision, astronomers can test whether subtle deviations from general relativity exist, perhaps hinting at quantum gravitational effects or alternative theories of gravity. Time dilation provides yet another window into testing theories. S2's rapid motion and proximity to a supermassive mass mean that time ticks slightly slower for the star than for us on Earth. By combining measurements of its velocity, light shifts, and orbital path, scientists can quantify this effect with extraordinary accuracy. If S2's observed time dilation ever deviated from predictions, it could indicate new physics beyond general relativity, such as the influence of higher dimensions or unknown gravitational interactions. S2 also enables testing light bending and relativistic lensing. The path of photons emitted by the star curves as they pass through the warped spacetime near Sagittarius A. By measuring tiny positional shifts in S2's apparent location on the sky, astronomers can compare real-world data to theoretical models. Even minute discrepancies could reveal the limits of Einstein's theory under strong field conditions or suggest additional mass distributions affecting spacetime curvature. Beyond confirming Einstein, S2 challenges theorists to account for higher-order relativistic effects. In extreme gravity, predictions become more complex. Orbital precession interacts with velocity-dependent time dilation, gravitational lensing, and redshift, creating a multidimensional system of relativistic phenomena. Continuous, high-precision measurements of S2 allow scientists to refine their models, testing calculations that are impossible to verify in any other context. Each orbit becomes a set of simultaneous experiments in extreme physics, with results that either reinforce or subtly adjust our understanding of gravity. The potential for S2 to reveal new physics is profound. If any deviation from expected motion, redshift, or time dilation were observed, it could point to phenomena like dark matter clumps near the black hole, interactions with other unseen stars, or even hints of modifications to general relativity in strong gravitational fields. S2 is unique in this regard. No other star in the galaxy approaches the black hole closely enough to produce such measurable relativistic effects, and no laboratory can replicate these conditions. Ultimately, S2 acts as a natural stress test for Einstein's equations. Each orbit is a confirmation, each close approach a critical checkpoint, and each measured anomaly a potential doorway to deeper understanding. Its extreme environment forces theory to confront reality in the harshest of conditions, providing scientists with data that cannot be simulated or replicated elsewhere. In this way, S2 is both a guardian of established physics and a probe for new frontiers, continuously challenging our understanding of the cosmos while solidifying the foundation upon which modern gravitational theory stands. The study of S2 has not only deepened our understanding of the Milky Way's central black hole but has also paved the way for the next generation of black hole science. By meticulously tracking its orbit and observing the relativistic effects it experiences, astronomers have developed a detailed model of the environment around Sagittarius A. This knowledge is directly informing cutting-edge projects, including groundbreaking initiatives like the Event Horizon Telescope, EHT, which aims to image black holes directly and probe their immediate surroundings with unprecedented resolution. S2 provides crucial context for interpreting the data collected by the EHT. While the telescope array itself focuses on the event horizon, the point of no return where light can no longer escape the black hole, S2 acts as a natural tracer of the black hole's gravitational influence. Its orbit defines the location and mass of Sagittarius A with high precision, providing essential coordinates and constraints that help the EHT team calibrate observations and refine the models used to interpret the shadow of the black hole. Without S2's decades of tracking, the EHT would be trying to image a largely unknown target, with far less certainty about the gravitational environment surrounding it. Furthermore, the study of S2 complements efforts to understand accretion flows and relativistic jets near supermassive black holes. While S2 itself does not produce these features, its movement through the intense gravitational field informs models of how matter behaves near such extreme objects. Observations of the star's velocity, gravitational redshift, and orbital precession help scientists simulate the motion of gas and dust spiraling toward the black hole. These simulations are critical for interpreting the faint radio signals and dynamic structures captured by the EHT, allowing astronomers to compare theory with observation in a direct, quantitative way. S2 also highlights the importance of multi-wavelength observation in black hole science. While the Event Horizon Telescope observes in the radio spectrum, S2 has been primarily studied in infrared. Combining these data streams allows researchers to connect the small-scale physics near the event horizon with the broader stellar environment, creating a more comprehensive picture of the galactic center. Essentially, S2 acts as a bridge between the larger-scale gravitational mapping of the black hole's influence and the fine-scale imaging of the black hole's shadow itself. Looking ahead, S2's continued observation promises to enhance future missions and discoveries. Every orbit provides fresh opportunities to measure relativistic effects more precisely, refine the black hole's mass and spin estimates, and identify subtle perturbations in the surrounding stellar population. This long-term dataset is invaluable for ongoing projects, including future expansions of the Event Horizon Telescope network, space-based interferometry missions, and next-generation infrared observatories. By anchoring these observations with reliable, measurable benchmarks, S2 ensures that theoretical models remain grounded in observable reality. Moreover, S2 serves as a testbed for new physics near the black hole. As observational technology improves, we may detect even finer relativistic effects, such as higher-order gravitational lensing, frame dragging caused by the black hole's spin, or minute anomalies in orbital precession. Each of these discoveries would not only refine our understanding of Sagittarius A but could also influence the interpretation of black holes throughout the universe, extending the lessons learned from our galactic center to distant quasars and active galactic nuclei. The legacy of S2 thus extends beyond its immediate orbit. By acting as a natural laboratory for extreme physics, it provides a foundation for the next wave of astronomical discovery. The precise measurements of its motion give scientists confidence in locating and understanding the black hole, while its relativistic behavior challenges and verifies our theories. As the Event Horizon Telescope and other missions continue to push the boundaries of what we can see, S2 ensures that we not only capture images but also understand the forces and physics shaping them. In essence, S2 bridges the gap between theory and observation, between the large-scale mapping of the galactic center and the intimate imaging of a black hole's edge. Its study informs the design, calibration, and interpretation of modern black hole science, ensuring that humanity's gaze into the darkest corners of the cosmos is guided by precision, context, and decades of accumulated knowledge. Without S2, our picture of Sagittarius A would be incomplete. With it, we have a dynamic, living model that connects the invisible structure of our galaxy to the very edge of spacetime itself. S2 is more than just a star orbiting a luminous guide that has transformed the way humanity understands gravity, spacetime, and the extreme physics at the heart of our galaxy. Before S2's careful observation, the center of the Milky Way was largely a mystery, a dense, invisible region obscured by dust, its gravitational forces inferred but never directly measured. The star's tight, high-speed orbit around Sagittarius A has changed that, offering a rare opportunity to study the dynamics of a supermassive black hole and the structure of spacetime in its vicinity. Through decades of precise observation, S2 has become a natural laboratory for extreme gravity. Its motion, light, and interactions with the black hole reveal effects that were once purely theoretical: gravitational redshift, time dilation, light bending, and orbital precession. These phenomena, predicted by Einstein over a century ago, are now observed and measured in real time thanks to S2. In this sense, the star is a bridge between theoretical physics and observational astronomy, allowing us to test our most fundamental theories under conditions impossible to replicate on Earth. By serving as this cosmic laboratory, S2 provides a stepping stone for future exploration of the universe. Understanding its orbit gives us insights into how matter behaves in the extreme gravitational field of a supermassive black hole, which in turn informs models of galactic evolution, black hole growth, and the dynamics of dense stellar environments. Every close pass of S2 tests our understanding of gravity at a scale and intensity unmatched elsewhere, making it a reference point for both current and future generations of scientists. S2's role as a gateway extends beyond the Milky Way. By demonstrating that relativistic effects are measurable in a star orbiting a supermassive black hole, S2 lays the groundwork for studying similar systems in other galaxies. The methods developed to track and analyze S2, adaptive optics, infrared imaging, spectroscopy, and long-term astrometry, can be applied to distant stars orbiting black holes across the cosmos. In this way, S2 is not just a subject of study, it is a template for exploring the universe's most extreme environments. Moreover, S2 brings the abstract concept of spacetime to life. Its orbit illustrates how mass bends the fabric of the universe, how time itself can pass differently depending on gravity and velocity, and how light follows curved paths under extreme forces. These are not abstract diagrams in textbooks, they are measurable, observable phenomena, and S2 makes them tangible. It provides a concrete example of how Einstein's equations manifest in reality, turning theoretical physics into a story we can witness unfolding in the sky. The star also serves as a beacon of inspiration and curiosity. Observing S2 reminds humanity that even in the darkest, most seemingly inaccessible regions of space, there is structure, predictability, and information to be uncovered. It shows that patient observation, advanced technology, and careful analysis can reveal secrets hidden behind layers of dust and darkness. For young scientists, students, and enthusiasts, S2 represents the promise of discovery, a reminder that even the most distant and extreme corners of the universe are not beyond our reach. S2's orbit is also a gateway to understanding the relationship between gravity and time, one of the most profound insights of modern physics. By measuring the star's time dilation, astronomers are not only confirming general relativity but also exploring the limits of our knowledge about the fundamental workings of the universe. Each measurement, each pass, each carefully calibrated observation provides a step forward in humanity's quest to comprehend the deepest principles of nature. In a broader sense, S2 exemplifies the power of observational perseverance. Decades of tracking, analysis, and interpretation were required to transform a faint point of light in the galactic center into a precise tool for scientific discovery. The star's orbit is a living record of human ingenuity, technological progress, and our relentless curiosity about the universe. In studying S2, we not only probe the nature of black holes and spacetime but also demonstrate the incredible potential of human inquiry. Ultimately, S2 is a gateway to knowledge about the universe itself. It bridges the visible and invisible, the measurable and theoretical, connecting our understanding of physics on Earth to the extreme realities of the galactic core. Each orbit provides new data, new confirmations, and sometimes new questions. It reminds us that the cosmos is not static, it is dynamic, extreme, and rich with phenomena waiting to be discovered. Through S2, we gain not just insights into a star or a black hole but a deeper understanding of gravity, time, and the very nature of the universe. S2 has earned the nickname the Immortal Star, and the moniker is more than poetic. It reflects the star's incredible resilience in the face of one of the most extreme environments in the galaxy. Orbiting perilously close to Sagittarius A, it repeatedly brushes past the supermassive black hole at speeds of thousands of kilometers per second, subjecting itself to gravitational forces so intense that any ordinary star venturing that close might be torn apart, consumed, or stretched into oblivion. Yet, S2 survives each pass with remarkable stability, maintaining its orbit like a fearless traveler skimming the edge of a cosmic abyss. The star's survival is extraordinary because the black hole's tidal forces near its pericenter are extreme. At a distance of roughly 17 light-hours, closer than the orbit of Uranus in our solar system relative to the Sun, the gradient in gravitational pull between the side of the star nearest the black hole and the side farthest from it is enormous. This differential, called a tidal force, is strong enough in many situations to rip apart stars or at least significantly deform them. Yet S2 endures. Its structure, mass, and orbital velocity combine to withstand the gravitational stresses, allowing it to repeatedly orbit the black hole without being destroyed. The Immortal nickname also speaks to the star's unbroken observational record. Astronomers have followed S2 for decades, watching it complete at least one full orbit since its discovery in the 1990s. Its repeated passages near Sagittarius A have been a continuous source of data, offering unparalleled opportunities to test Einstein's theory of relativity, study gravitational redshift, and observe time dilation. In a sense, S2's resilience allows it to act as a perpetual cosmic laboratory, maintaining its orbit long enough for humanity to conduct experiments that could not otherwise be performed. There is also an element of drama in the nickname. S2 dances on the edge of destruction, orbiting a black hole whose gravitational pull is absolute and whose influence dominates the center of the galaxy. Each close approach could, theoretically, have ended differently. If the star had been slightly closer or slightly slower, the black hole's pull might have drawn it past the point of no return. Instead, S2 survives pass after pass, a stellar daredevil enduring conditions that push the limits of physics. Its resilience inspires awe, and calling it immortal captures both its physical endurance and the sense of wonder it evokes. Interestingly, the nickname also underscores the timescale of cosmic events. While S2 is far from eternal in an absolute sense, it will eventually exhaust its nuclear fuel and evolve like any other star. On human timescales, it appears almost indestructible. Over decades of observation, the star's orbit remains intact. Its structure unchanged, and its motion predictable, giving it the appearance of timelessness in an environment dominated by chaos and immense gravitational forces. The Immortal moniker is further reinforced by the star's symbolic role in science. Just as it survives the black hole's immense pull, it also survives the scrutiny of decades of observation and analysis. Each orbital pass reaffirms predictions, confirms models, and withstands the rigorous tests of astrophysical investigation. In this sense, its immortality is as much about its scientific utility as its physical endurance. S2 continues to live in our telescopes and in our understanding of extreme gravity, providing insights that no other single star in the galaxy can match. Finally, S2's nickname captures the imagination, helping to convey the drama of its environment to the public. The phrase Immortal Star evokes images of a celestial survivor, a beacon of light and resilience circling a dark, all-consuming force. It reminds us that in the universe, there are not only destructive extremes but also incredible endurance. S2's continued existence is a testament to the delicate balance of forces that govern stellar dynamics near supermassive black holes, and it serves as a vivid, almost mythical symbol of persistence at the very edge of space-time. In short, S2 is called immortal because it has survived repeated close brushes with one of the most destructive objects in the galaxy, enduring tidal forces and gravitational stresses that would obliterate most stars. Its survival allows it to continue as both a physical object and a scientific tool, orbiting Sagittarius A with incredible regularity while providing humanity with a front-row seat to some of the most extreme physics in the universe. The name Immortal is a perfect reflection of its resilience, its ongoing contribution to science, and the awe it inspires as it dances perpetually on the edge of destruction. Despite its perilously close passes around Sagittarius A, S2 is extremely unlikely to ever be swallowed by the black hole, and its continued survival is a result of the delicate balance between its velocity, orbit, and the immense gravity that both threatens and stabilizes it. At first glance, it might seem almost miraculous that a star can approach a supermassive black hole so closely without being consumed. The answer lies in the dynamics of orbital mechanics and the nature of supermassive black holes themselves. S2 follows an elliptical orbit with a pericentre distance of about 17 light-hours. This distance, while extremely close on a galactic scale, is still far enough that the star's orbital velocity keeps it in stable motion rather than letting it spiral into the black hole. Essentially, the faster a star moves at its closest approach, the more centrifugal force counteracts the pull of gravity. S2's speed of roughly 7,650 km per second during pericentre ensures that it slingshots around Sagittarius A, following a highly elongated path rather than being drawn directly inward. Its velocity is finely tuned by the laws of physics. If it were slower, it might risk falling in, and if faster, it would follow a less bound trajectory. The concept of tidal forces also plays a role. While the gravity near Sagittarius A is extreme, S2 is still outside the black hole's Roche limit, the distance at which tidal forces would tear a star apart. Supermassive black holes, despite their enormous mass, exert these destructive tidal forces only very close to the event horizon. Because Sagittarius A is so massive and relatively compact, the Roche limit for a star like S2 lies well within its actual pericenter. This means that, although the star experiences immense gravitational stress, it is not in danger of being shredded. Its structural integrity remains intact throughout its orbit. Another stabilizing factor is the predictability of S2's orbit. Unlike objects on chaotic trajectories, S2 is influenced primarily by the central black hole, with minimal perturbation from surrounding stars or gas. Its path is highly regular, and the gravitational dominance of Sagittarius A ensures that S2 continues in a stable elliptical orbit rather than being deflected into a collision course. This stability is why astronomers can predict its position decades into the future and why the star survives repeated close approaches. It is also worth noting that S2 is orbiting a supermassive, not stellar mass, black hole. Smaller black holes can exert intense tidal forces at relatively large distances, posing a greater immediate threat to nearby stars. Sagittarius A, by contrast, has a mass of about 4 million suns. Its gravitational gradient over the distance of S2's pericenter is extreme but smooth, which allows stars in stable orbits to survive near it. The black hole's sheer size spreads out the tidal effects over a longer distance, paradoxically making it possible for stars like S2 to orbit close without immediate destruction. In theory, there are scenarios in which S2's orbit could be altered, such as a close encounter with another massive star or a dense gas cloud that nudges its trajectory. However, such interactions are rare in the crowded but well-modeled environment of the galactic center. Even if a small perturbation occurred, it would need to be precise and significant to send S2 on a collision course with Sagittarius A. For now, all observations indicate that its orbit is remarkably stable, and it will continue circling the black hole for many thousands, if not millions, of years. S2 stability also underscores the difference between orbital mechanics and direct infall. Stars do not simply fall into black holes unless they lose sufficient angular momentum. S2's elliptical orbit preserves its angular momentum, preventing it from spiraling inward. The black hole's gravity bends its path but does not pull it straight in. Its orbit is a careful cosmic balance, a dance dictated by gravity, velocity, and distance, which keeps the star perpetually on the edge but never crossing the point of no return. Ultimately, S2's continued survival illustrates the remarkable interplay of physics near a supermassive black hole. Its velocity, orbit, and distance create a stable system that allows it to endure repeated close encounters with a force that could easily destroy a lesser star. While no star is truly immortal on cosmic timescales, S2 demonstrates that under the right conditions, stars can exist in extreme gravitational environments without being swallowed, orbiting perilously close to one of the universe's most powerful objects with elegance and stability. To truly grasp the drama of S2's journey, it helps to put its orbit into the context of the Milky Way. Our galaxy is a sprawling spiral, stretching roughly 100,000 light-years across, with hundreds of billions of stars orbiting its center in relatively stable paths. The Sun, for example, sits about 26,000 light-years from the galactic center and completes a single orbit in roughly 225 million years, moving at a speed of approximately 220 kilometers per second. Compared to S2, Earth's path seems almost leisurely, a gentle orbit far removed from the extreme forces dominating the galaxy's heart. S2, by contrast, is a star living at the very edge of cosmic peril. Its orbit brings it within just 17 light-hours of Sagittarius A, an almost unimaginable proximity. To put this in perspective, the distance between the Sun and Mercury is about 0.4 astronomical units, roughly 17 light-minutes. S2's closest approach to the black hole is about 60 times larger than the Sun-Mercury distance, yet in galactic terms, it is an extraordinarily tight orbit, circling a mass millions of times greater than our Sun. While the Sun's orbit is governed by a smooth, comparatively weak gravitational field, S2's trajectory is dominated by intense spacetime curvature, tidal forces, and extreme velocity. The contrast becomes even more striking when considering speed. Earth travels around the Sun at roughly 30 kilometers per second. S2, during its closest approach to the black hole, rockets along at 7,650 kilometers per second, about 3% of the speed of light. This is more than 250 times faster than Earth, highlighting the scale of energy and gravitational influence at play. While we trace a near-circular path in a tranquil orbit around a relatively light star, S2 is a cosmic daredevil, racing along a highly elongated ellipse in a region where relativity dominates the rules of motion. Even the timescales amplify this difference. The Sun completes a single orbit around the galactic center in hundreds of millions of years. S2 completes its orbit in just 16 years. From a human perspective, this makes S2's life a compressed story of extreme physics. Each orbit is a lifetime of experience near a supermassive black hole, a full cycle of gravitational stress, velocity extremes, and relativistic effects condensed into decades. In the cosmic timeline, S2 lives on fast forward, allowing astronomers to witness phenomena that, for stars like the Sun, would take millions of years to unfold. Looking at the Milky Way as a whole, S2's orbit is minuscule yet intensely significant. If we imagine the galaxy as a massive clock, Earth is a slow-moving hand tracing a wide circle, while S2 is a needle spinning wildly near the center, tracing a high-speed path around the galactic fulcrum. The black hole's mass dominates the region, dwarfing all nearby stars, and S2 responds to its pull with precision, velocity, and grace, offering a glimpse of the immense energies at play in galactic cores across the universe. Placing S2 in this cosmic context emphasizes the contrast between the calm, familiar solar neighborhood and the violent, energetic heart of the Milky Way. We live in a relatively safe zone, far from the intense gravity and high-speed dynamics of the galactic center. S2, on the other hand, experiences forces so extreme that they bend light, distort time, and stretch space itself. Its orbit reminds us that the galaxy is not uniform. It is a complex tapestry where environments range from the placid to the catastrophic. Finally, the comparison underscores the remarkable observational opportunity S2 provides. Being relatively close in human terms, just tens of thousands of light-years away, it allows scientists to study a supermassive black hole in detail, in contrast to distant galaxies where even the most advanced telescopes can only hint at the presence of such objects. S2 acts as a cosmic magnifying glass, focusing the drama of extreme gravity into a measurable, understandable system, and providing a reference point that anchors our understanding of galactic dynamics on both a local and universal scale. In essence, S2's orbit transforms the center of the Milky Way from a distant, abstract concept into a theater of extreme physics. While we orbit our Sun in comfort, S2 circles a titanic black hole at incredible speed, surviving immense forces that dwarf anything in our solar neighborhood. By comparing our place in the galaxy to S2's perilous path, we gain perspective on the cosmic scales, the energy involved, and the extraordinary resilience of this immortal star, highlighting just how dramatic and extreme the heart of our galaxy truly is. To truly connect with the scale and drama of S2's orbit, it helps to imagine a human perspective, what it would be like to stand on a planet orbiting this extraordinary star. Picture yourself on the surface of a world circling S2, tens of thousands of times closer to the galactic center than Earth is, with the immense presence of Sagittarius A looming in the sky. The familiar comforts of a solar system orbiting a quiet star would vanish, replaced by a celestial scene of unimaginable power and intensity. From such a vantage point, the black hole would dominate the heavens. Unlike our Sun, which appears as a bright disk but is safely distant, Sagittarius A would appear as a massive, dark void, surrounded by a distorted halo of light from the warped spacetime around it. The sky would not be a simple black canvas punctuated by distant stars. It would be a dynamic theater of relativistic phenomena. Light from the surrounding galactic center would bend and stretch, creating arcs, rings, and warps as gravity distorts its path. The familiar constellations of the Milky Way, as we see them from Earth, would be twisted and smeared by the extreme gravity of the black hole. Time itself would feel different near S2. On a planet orbiting this star, relativistic time dilation would be perceptible in principle. A clock on the surface would tick slightly faster than one observed from afar, while observers on distant worlds would perceive time differently as S2 zipped along its high-speed orbit. Every second of local time would carry the imprint of extreme gravity, reminding any hypothetical observer that the laws of physics here are not the same as the calm, steady environment we take for granted on Earth. The star itself would be a brilliant beacon, its light intense and close, yet under constant gravitational strain. As S2 swings past Center, Its velocity and proximity to the black hole would produce subtle fluctuations in brightness, with light stretched and warped in ways that would make the star shimmer and pulse from the perspective of a nearby planet. The gravitational lensing from Sagittarius A could magnify background stars or distort their positions, creating a constantly shifting panorama of the galactic center. From this vantage point, one could witness the curvature of space and the warping of light with their own eyes, a cosmic ballet that turns abstract physics into a tangible, visible spectacle. Even the broader universe would appear differently. The galaxy, seen from this inner orbit, would no longer be a calm spiral but a dense, crowded, and energetic environment. High-velocity stars like S2 trace paths through this gravitational maelstrom, while gas clouds swirl and collide under the influence of the central black hole. One could observe, in miniature and in real time, the forces that shape the evolution of galaxies, from the orbit of a single star to the dynamics of entire stellar populations. This perspective also emphasizes the fragility and precision of S2's orbit. Observers on a nearby planet would feel the immense forces at play, understanding that the star's stability is not guaranteed forever. It is the result of a precise balance between velocity and gravity. The immortal moniker would feel visceral. One could witness, in principle, the delicate cosmic dance that keeps S2 from being consumed by the black hole, a stellar tightrope act performed in extreme conditions. From a human standpoint, imagining life on such a planet underscores both the awe-inspiring and humbling aspects of the universe. It reminds us how ordinary our solar system is, orbiting a relatively calm star far from the cataclysmic forces at the Milky Way center. At the same time, it allows us to appreciate the bravery of S2, not in conscious terms, of course, but in its persistence against the odds, as a natural sentinel circling one of the most powerful objects in existence. The star's orbit becomes not just a scientific marvel but a cosmic story, connecting human imagination to the extreme realities of astrophysics. Through this lens, the study of S2 gains a profound human dimension. It is no longer only a point of light in an infrared telescope. It becomes a place, a stage, and a symbol. It allows us to picture ourselves in the extreme environment of the galactic center, seeing firsthand the effects of gravity and relativity, experiencing the drama of a star on the edge, and witnessing the unimaginable scale and power of a supermassive black hole. This mental exercise brings the universe closer, bridging the gap between observation and experience, and reinforcing the wonder that drives the scientific pursuit of stars like S2. S2 is far more than a distant point of light orbiting an invisible giant. It is a messenger from the edge of spacetime, a natural laboratory, and a cosmic storyteller, revealing the universe in ways that no telescope or experiment could replicate alone. Every swing of its orbit around Sagittarius A conveys messages about gravity, time, and the deep structure of our galaxy. Through S2, we witness the subtle yet profound consequences of Einstein's relativity, the immense power of a supermassive black hole, and the delicate balance that allows a star to survive where so many others would perish. Each close pass is a reminder of the extremes of nature. S2 skirts the edge of destruction, hurtling at thousands of kilometers per second through the warped fabric of spacetime. Its light stretches and bends, its orbit shifts imperceptibly, and time itself flows differently in its vicinity. Observing these phenomena transforms abstract physics into tangible reality. We are no longer limited to imagining equations on a page. We can see, measure, and quantify the forces that govern the cosmos. S2 is a bridge between theory and observation, between the invisible and the knowable, and between human curiosity and the universe's most profound truths. S2 also embodies the courage of exploration, not in a conscious sense, but as a stellar participant in the grand dance of the cosmos. Its orbit challenges us to expand our understanding, to confront conditions that defy everyday experience, and to probe the boundaries of physics. By tracking S2, we have been able to test fundamental theories, map the galactic center, and glimpse the interplay of mass, light, and time in one of the most extreme environments imaginable. It teaches us patience, precision, and the value of long-term scientific dedication, showing that even phenomena occurring 26,000 light-years away can illuminate universal truths. Viewed on a cosmic scale, S2 is both tiny and monumental. It is a single star among billions, yet its significance is extraordinary. It survives near a supermassive black hole, it encodes the physics of extreme gravity in its motion, and it offers humanity a window into processes that shape entire galaxies. In this sense, S2 is a messenger, not just of science, but of perspective. It reminds us how vast the universe is, how powerful its forces can be, and how capable human curiosity is when guided by observation, ingenuity, and determination. S2's story is ongoing. Each orbit, each observation, and each measurement adds new chapters to our understanding. Future astronomers will continue to study its motion, refine their models of relativistic physics, and perhaps even detect subtle anomalies that point to unknown aspects of gravity or the structure of the universe. It is a star that teaches across generations, linking the earliest discoveries in the 1990s to the most cutting-edge research of the 21st century and beyond. Ultimately, S2 invites awe and wonder. It is a stellar ambassador at the boundary of known physics, orbiting a gravitational titan that dominates the heart of our galaxy. It shows us how light bends, how time stretches, and how matter dances around one of the universe's most extreme objects. It exemplifies the interplay between risk and stability, motion and mass, energy and gravity. And through it, humanity gains not only knowledge but perspective, a sense of our place in a universe far larger, stranger, and more intricate than we can fully imagine. S2 is not just a star, it is a guidepost, a teacher, and a witness. It communicates the elegance and brutality of cosmic laws and reveals the hidden structure of the Milky Way. Standing on the metaphorical threshold of its orbit, we are reminded that the universe is not static. It is dynamic, extreme, and full of lessons waiting to be discovered. Through S2, we see the invisible made visible, the extreme made measurable, and the theoretical made tangible. It is, in every sense, a messenger from the edge of spacetime, whispering the secrets of the cosmos and showing us, star by star, orbit by orbit, how the universe truly works. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.